Let's look at how to use a pKa table. Remember from general chemistry that pKa is equal to the negative log of the Ka, and the lower the pKa value, the stronger the acid. pKa values are used a lot in organic chemistry, so it's really important to become familiar with them. For example, if our acid is HCl, the pKa of this proton is approximately -7. So if a base comes along, some generic base, and takes this proton, these electrons are left behind on the chlorine. So let's use a different color here. So the electrons in magenta come off onto the chlorine to form the chloride anion. So the chloride anion is the conjugate base to HCl. The lower the pKa value, the stronger the acid. And out of all the acids I have on this pKa table, HCl has the lowest pKa value. So this is the strongest acid out of the ones on this pKa table. And from general chemistry, the stronger the acid, the weaker the conjugate base. Because for an acid to be strong, the conjugate base must be weak to resist reprotonation. If it's easy to lose a proton, it should be really hard to regain it. Otherwise, you wouldn't have a strong acid. So HCl has the lowest pKa value on this table, so it is the strongest acid. And the chloride anion must therefore be the weakest base out of all of the conjugate bases on the right side of our table. Next, let's look at this acid. So this is the acidic proton. So if a base came along, some generic base, and took this proton and left these electrons behind on the oxygen, we will use this color again. So the electrons in magenta come off onto the oxygen to give us acetone as our conjugate base. The approximate pKa for this proton is -3, and I've seen lots of different pKa values for this proton. I've seen -6, I've seen -7. So use whatever pKa values you are given in your course. So pKa tables don't always match exactly, and this is one that I've seen lots of different values for. Next we have hydronium, H3O+. So if a base comes along and takes a proton from hydronium, the pKa of that proton is approximately -2. So these electrons would come off onto the oxygen. So the electrons in magenta come off onto the oxygen, and those would be these electrons right here to form water as our conjugate base. So H3O+ has a higher pKa value than HCl. Therefore, H3O+ is not as strong of an acid. Or we could say it the other way around. HCl has a lower value for the pKa. Therefore, HCl is a stronger acid than H3O+. All right, let's look at some more examples for acids and pKa values. So next, let's look at acetic acid. So this compound right here, here's the acidic proton on acetic acid, and that proton has a pKa value of approximately 5. So if a base takes that proton, these electrons are left behind on the oxygen, which give that oxygen a -1 formal charge. So the acetate anion is the conjugate base to acetic acid. Next, our next compound, we have these two protons right here, and let's say this proton, it doesn't really matter which one you choose, has a pKa value of approximately 9. So if a base takes that proton, then the electrons in magenta here are left behind on a carbon. Let me go ahead and circle the carbon. So this carbon would get a -1 formal charge. Our next compound is phenol, and the acidic proton on phenol is this one right here. So if a base takes that proton, these electrons in magenta are left behind on the oxygen, which give the oxygen a -1 formal charge. So this is our conjugate base. So the pKa for that proton is approximately 10. All right, let's get some more space down here. Let's look at some more. All right, next we have water. Right, so what's the pKa for this proton on water? It's approximately 15.7. So the conjugate base to water would be hydroxide. Next we have ethanol. So this is the acidic proton on ethanol. The pKa value is approximately 16. So the electrons in magenta here would end up on the oxygen, giving the oxygen a -1 formal charge. So this is the ethoxide anion. So how much more acidic is phenol than ethanol? Remember, the lower the pKa value, the stronger the acid. Phenol has a pKa value of 10 for this proton, whereas ethanol has a pKa value of 16 approximately for this proton. So how much more acidic is this compound compared to this compound? Well, remember the definition for pKa. It's the negative log of the Ka. And each pKa unit is an order of magnitude. So how many units difference do we have between these pKa values? This one's 10 and this one's 16. So that's a difference of 6. But really, each unit is an order of magnitude. So this proton on phenol is 10 to the 6th times more acidic. So this compound is 1 million times more acidic than ethanol. So that's really how to think about acid strength when you're looking at a pKa table. And it's so much easier to work with pKa values, which is why they're used so often in organic chemistry. All right, next, let's look at another alcohol. So this proton has a pKa value of approximately 17, and this would be the conjugate base. This proton on this next alcohol, the pKa is approximately 18, so we get this as our conjugate base. And we'll talk about the reasons why. For example, we have these alcohols here. Later, we'll talk about the reasons why they have different pKa values. All right, let's look at some more. So the pKa value for this proton is approximately 19. So if the base comes along and takes that proton that I just circled in red, these electrons in magenta would be these electrons, and they're on this carbon now, which gives that carbon a -1 formal charge. All right, next we have acetylene, right? So if we deprotonate acetylene, this pKa has a value of approximately 25. So the electrons in magenta here are left behind on this carbon to give us the conjugate base. All right, for ammonia, if a base took that proton, these electrons would come off onto the nitrogen, so that would be these electrons here, giving us our conjugate base with a pKa value of approximately 36. And this is another compound you see a lot of different pKa values for. I've seen 33, I've seen 38. So again, use whatever pKa values you are given in your class. All right, let's finish this off here. So our last few compounds. So what's the pKa for this proton? It's approximately 44. So the electrons in magenta come off onto your carbon, and this would be your conjugate base. And our last example, ethane, is the weakest acid out of all of the acids I have listed on this pKa table. So the pKa for this proton, approximately 50. And the electrons in magenta here would be left behind on this carbon. So if this is the weakest acid, right, if ethane is the weakest acid, then this must be on the right here. This must be our strongest base. So you can also use a pKa table to think about the strengths of bases. So if you had some acid here, let me go ahead and draw one. So HA right here, right? So the electrons in magenta would take this proton, and these electrons would be left behind. And so you would reprotonate. You would form your ethane, right? So if this functioned as a base and took a proton, then you would make your ethane here. So the stronger the base, the weaker the conjugate acid. So pKa tables are important for thinking about the strengths of acids, and you can also use them to think about the strengths of bases.